So it's a pleasure to be here. This is basically my first activity post COVID. So it's really nice to be able to talk with people again. And so yesterday I made a poll, a quick poll to see what you were interested about, and surprisingly, you decided to go for the let's say more complicated models. So well, now if it feels a little bit overwhelming, it's your fault. but that doesn't mean that you cannot ask questions. Okay, so please go ahead, ask questions, make comments, because that's one of the main features that we are really missing after 2 years of online lectures, right? So let me see, what do we have today? Okay, yes, so the so-called reaction-diffusion model. Okay, so I'm going to define particular instance of what is known as reaction-diffusion models in the literature, and it's a type of interacting particle systems, and an interacting particle system is a very particular subclass of Markov chains. Okay, and it's a very important subclass of Markov chains, and they have somehow the same their own language. So I'm going to give you in a few minutes, maybe 15-20 minutes, a crash course on interacting particle systems notation. Okay, so we understand a little bit better what we are going to talk about. So in not necessarily, but when you want to discuss large scaling limits of this type of Markov chains of interacting particle systems, maybe I just remove there is a scaling parameter. Okay, so there is that I'm going to call n. Some people call it epsilon. It doesn't really matter. It's a parameter that is, in this case, n is a natural number goes to infinity, and it's going to represent the 1 over n is going to be the mesh of our system. Okay, so this is we're thinking about a discrete system that approximates a continuous system in some way. And we are thinking about, for example, in the lattice, that the distance, the unit distance on the lattice become distance is 1 over n in the continuum. Okay, so usually when talk about particle system, there is a set Q, which is the set of particle states. Okay, so for example, in the Ising model that Hendrik was discussing yesterday, the Q was plus 1 and minus 1. So for example, we saw today, I think it was Francis, maybe, he was talking about these diffusions, and then the particle states were 0, 1, and 2. So you can choose different type of particle states depending on what you're interested in. Okay, so nowadays something that it become more popular, for example, is the seed model, no, where you have actually the set Q is composed by the letters S, I, and R for susceptible, infected, and recovered. No? And there are these compartment models on which you put more letters because, well, you want to maybe model better and add more features to your particular model, and that's what you do with this set Q. Okay, so those are the particle states, and these particles, they live somewhere in some geometrical underlying space, and in our case, what we are going to take as the geometric underlying space is the discrete torus. Okay, to make things keep things simple, I really want to stick to finite state Markov chains, and so in particular, I want a finite set, and the simplest finite set that has some nice structure is the periodic lattice. Okay, and then. So you see here that so the space state of an interacting particle system now is this set omega n, which is q to the power lambda n. Okay, lambda n is the discrete torus, q are the particle states, and you see that in this case this set is enormous. No, it has a size 2 to the n to the d, right? So the main feature of interacting particle system is that they're finite state Markov chains that live in a huge state space, right? So today, someone was showing simulations, no, on a 60 by 60 grid, and you can compute, no, 60 by 60, 360, 2 to this. That's enormous numbers. Okay, so in our case, in our reaction diffusion model, the states are going to be empty and occupied. Okay, so 0 means empty and 1 means occupied. Well, in other situations, you can take other different states. Now, in a spin model, the states are plus or minus that represent the spin up, and down, and you can generalize in various different ways. Okay, so when you look at the interacting particle system, so one way to think about them is to think about local transformations. Okay, so what is a local transformation? Is something that only changes your configuration of particles in a small neighborhood of the whole system. So, for example, now here you have the particles living in the discrete torus ZDN, which is very big, and what you're going to do is that this local transformations only changes the configuration in maybe one side, maybe two sides, maybe 3/4 sides, but a fixed small number of sides. Okay, so for example, in these spin systems, you only change one side per time. So in what Christina was talking about, in what is called the exclusion process, you change 2 sides per time. In the sand pile, sometimes you change maybe 4 sides because you have a pile of 4 guys. You topple the pile and you change well, 5 guys, 2n plus 1, 2d plus 1. Anyway, a finite number of guys. Okay, so the local transformations are going to use to build up this reaction diffusion model are 2 types of local transformation. The first one is what I'm going to call flip. Okay, so what is a flip? It's a transformation that takes a configuration. So it's a map between omega n and omega n. Okay, it takes a configuration of particles and gives you a new configuration of particles. Okay, so they are parameterized by the elements of the underlying geometric space, so of x and lambda n, the sides, and so the definition is there. What you do is just that fx of sigma doesn't change sigma except at site x, where it just flips the value from 0 to 1 and from 1 to 0. That's what this transformation does. And we usually use a short form for this transformation. We call it sigma x with a superscript there. So that's just a shortcut. It's a short form for the flip of sigma at x, of fx of sigma. Okay, so these are transformations. Okay, so they take a configuration and change it to another configuration, and this transformation is local in the sense that only changes 1 or maybe 2 sites per time. Okay, so a second type of local transformation is what we call exchanges. Okay, so what is an exchange? So now these exchanges are parameterized by 2 parameters, which are 2 sides of the underlying lattice. Okay, so x and y. So here in my definition, x and y are arbitrary, so maybe you can change 2 sides which are far away in the underlying lattice. That's okay in terms of definition. But later on, we will specify that we are only going to consider neighboring sides. Okay, so it's going to be local in that sense. But even in the global sense, when you change when x and y are far away, you still can think this is just a local transformation because it changes something around only 2 neighborhoods of your system. So there are 2 distant places, but the changes in those 2 distant places are local. So I'm just giving a name, E of x, y of sigma. So it's another configuration, and it's if you evaluate it at site z, so at site z, it's equal to the original configuration unless z is equal to x or y. And what happened at x or y is usually a change. No? If there was a 0 at x and a 1 at y, now you have a 1 at x and a 0 at y, and vice versa. observe that sometimes this exchange transformation doesn't do anything, because if the two values at x and y were equal to begin with, when you exchange them, you get the same configuration again. Okay? Notice that although it's not going to be relevant for us, both transformation flips and exchanges are they have a name in algebra, I forgot, but so you apply it again and you get the identity. Okay, so those guys have a name in algebra that I forgot. Idempotent. Thank you. And well, that's not very relevant for our discussion here, but this property comes in handy if you want to check, for example, things like reversibility in some contexts. Okay. It's also nice that there is some algebra behind this underlying transformation that makes this interaction, many times these interaction particle systems amenable to algebraic methods. So of course, so in short form, this transformation EXY of sigma is going to be denoted by sigma XY, okay, with superscripts X and Y. Okay, so you see that these transformations can be parameterized by an index set, okay, that I'm going to call I. So the index set in this case is just is the set of points on my underlying geometric space lambda n, or the set of couples, and so these are unordered couples xy in lambda n. And usually what you do is that you take a subset of this index set as the transformations that you want to use to build up your interacting particle system. So what is an interacting particle system? So remember that so the generator of a Markov chain, this operator L, which is written down there, is just a linear operator that tells you more or less how much do you expect the function f to change under the evolution of the dynamics. Okay, so if you look at an interval of size delta n, you will see a jump from sigma to omega with probability, roughly speaking, approximately equal to delta times r of sigma omega. So that sum there represents how much you expect the function f to change in a small time interval. And well, this is the usual form on which you write the generator of a general Markov chain. Okay, you see that this sum here, for the case of interacting particle systems, is not very useful as a representation. Why? Because the sum I wrote there is over all omegas in the state space. That, remember, is a set of size of cardinality to the n to the d. So it's huge, no? So well, in the one-dimensional case, it's 2 to the n. In the d-dimensional case, it's 2 to the n to the d even larger. Okay, so this sum, it's a huge sum. Moreover, is full, in general for interacting particle systems, is full of zeros. Okay, why? Because in an interacting particle systems, what happens is that these rates r sigma omega are equal to 0 unless this omega can be obtained by from sigma by means of an allowed transformation. Okay, so in our case, so the allowed transformations are either flipping one side, so going from 0 to 1 or 1 to 0, or exchanging two sides. Okay, so in particular, for the reaction diffusion models, this example of interacting particle systems, the rate, this function r of sigma omega is equal to 0 if, for example, these two guys differ in more than two sides. Okay, so that means that this as a matrix, this number r is a very, very sparse matrix, right? Because you see that the cardinality of the set of indices. So here I wrote the one-dimensional case. It's n squared. Okay, so it's a number of of points of my underlying lattice plus the number of couple. And the cardinality of omega n of the state space is 2 to the n. So it's really a very sparse matrix. No? So it has only among the 2 to the n entries, there are only n to the square which are non-zero. Okay, now that means that this representation of the generator L in terms of the rates R is not the most convenient one for interacting particle system. Okay, so that's why to describe an interactive particle system, we do something different. Okay, so we write a function C of I. So remember that these I's are the index allowed in my index set. So it could be a point X, or it could be two guys X and Y. And these CIs are some functions. Okay, so positive functions, and defining. So they satisfy this relation. So Ci of sigma is just R of sigma sigma I. So it really is the probability of making the transition from the current configuration of the particle system to one of the transformed configuration. So in an interacting particle system, what happens is that you have a set of allowed transformations, and you take one of these transformations at random with some probabilities that depends on the configuration, the current configuration of the system, and you apply that. That's basically what an interacting particle system does. Okay. And in continuous time, of course, you don't talk about probabilities, you talk about rates, instantaneous rates. Okay, so the rates at which you perform this operation. Okay, so that's why when you describe an interacting particle system, it's more convenient to describe it in terms of this rate Ci. Okay, so this Ci is the rate at which the transformation I happens. And this is a better description because it's more concise. No, you see now we really have a sum with n to the square terms instead of a sum with 2 to the n terms. Okay, so that was our crash course on interacting particle system notation. And now let me tell you what it's the reaction diffusion model in a more precise way. Okay, so first I'm going to declare two guys on my lattice to be neighbors if they are neighbors, all right? Okay, so also if they are at distance 1 in the, for example, in the L1 norm. Okay, so the usual sense of neighbors of the integer lattice. Okay, and now my set of allowed transformations is going to include only couples which are neighbors. Okay, so I'm only going to make exchanges between neighbors, and then the flips, well, the flips are going to happen everywhere. Okay, so all sides can be flipped. And now let me tell you, let me write down the rates. Okay, so there are, in reaction diffusion models, there are two components: the reaction component and the diffusion component. Okay, so the simplest way to introduce the diffusion component is just to take these exchanges at constant rate. Okay, so that makes the system already diffusive, and so it's complicated enough to already manifest the type of behavior that we want to model in reaction diffusion equations. And maybe you want to complicate it more, but at least in a first discussion, it's always good to not complicate things too much. And there is an m squared there. So it's going to be a constant rate. So what is the value of this constant rate? So we're already going to introduce the diffusive timescale, right? Because we know that, for example, imagine that your particle configurations has only one particle at the beginning, right? In that case, this complicated exclusion process, this is what is generated by this rate Cxy, is just a simple random walk. And the simple random walk, we know that has interesting scaling limits in diffusive timescale. That's why the rate we're already taking it as diffusive, so we don't have to worry later on with rescaling time. Okay. And then, so well, sometimes people do these schematics. if I tell you Cxy is equal to n squared, so there is this other drawing here, no, that tells you that you do this transformation, no, in both directions. You do it at rate n squared. Okay, so now let me put reaction. Okay, so what is this reaction? Is the rate at which these flips occur. Okay, so if I really want to see something different, something in what we call non-equilibrium, this Cx of sigma cannot be just constant. Okay, because if it is just constant, the model is it's kind of linear, so it gets into linear in the realm of linear equations, and for in this case on which you have only one type of particles, the linear regime is not the most interesting one. Okay, so to make it non-linear, something that you can do is, for example, to take this right there. So this right there it's nice for two reasons. So first reason is that well, as I was telling you before, so nowadays everybody talks about epidemiologic models. So one very nice epidemiologic model is the contact process. Okay, and this rate is somehow reminiscent of the contact process. So you have it's what I call contact process with integration. Okay, because in this rate that I wrote here, so let's try to interpret what is going on. So this 1 minus sigma x means no particle at site x. So when there is there is no particle at site x, we are going to create a particle. Now that's what the flip does, with a rate which is it's proportional to the number of neighbors that we are occupied. So if we interpret these ones as infected individuals, that's exactly the contact process, right? So you get infected with a rate which is proportional to the number of infected individuals in your surroundings, and then you get recovered with rate b. Okay. So in order to make the model irreducible, we introduce the rate a. So you can get infected with probability a regardless of the configuration of your neighbors. Okay. So and that I usually call it integration, because it means that in your fixed population that you are studying, so on top of this fixed population, there is other population that you don't see that comes from outside world, no, and maybe they are infected and can infect you, and that's the role that is played by this number a in this interpretation of these rates as a methodological model. From a mathematical point of view, this type of rate is the simplest one that is that gives rise to a nonlinear evolution in the limit. Okay, so it's the simplest possible one. Okay, so I don't think there is something simpler. So schematically, you see it downstairs. So maybe so you can see then there are these. So I wrote these rates in a schematic way. So you create a particle with a rate which is equal to a plus lambda times the number of neighbors divided by the infected neighbors divided by the number of neighbors, and then you can recover with rate b. Okay, and the n square scaling here makes it makes this model a reaction-diffusion model, because in that case both parts, the diffusion and the reaction part, matter in the limit. So okay, if you try to describe the evolution of this system for large n, you need to take into account both guys. None dominates the other. So the reaction-diffusion model, so it's going to be the Markov chain generated by this generator which is there. So from this discussion with before, so you can read now this as in terms of this transformation. So the exchanges, each one of the exchanges happens independently at random with the exponential rate, the instantaneous rate n squared, and then each flip happens conditioned on the actual value of the chain independently at random with the instantaneous rate cx of sigma. Okay, and observe that. So you need all these ingredients to get an irreducible chain, because the exchanges alone they don't change the number of particles, which means that this set omega n is not irreducible for the chain with only exchanges, it's what we call the exclusion, the simple symmetric exclusion process. Okay, so it's not it's not irreducible, but well, you can still think about the irreducible components or something like that, but I don't really want to enter into that additional layer of complication. And then you also need creation and annihilation both to happen, because if you, for example, if you put this if you run this dynamics and you don't put immigration, only the usual contact process rates, what happens is that at someday all particles will disappear and the evolution ends up in a absorbing state. Okay, so it's not irreducible. You can also analyze this type of situations. It could be interesting as well. But for the discussion that we're having here, we're just assuming irreducibility to make things a little bit simpler. Okay, so this is a reaction diffusion model. Something that you can check. Let me see if I yeah, is that this chain is non-reversible. Okay, so there is no explicit formula, at least not known explicit formula for the invariant measures of this reaction diffusion model, and probably because there is none. No, so there is not an explicit formula. It's pretty natural because most of the chains don't have explicit invariant measures, especially if they are non-reversible. But you can check that the invariant measure is non-reversible. Okay, so that's what we call a non-equilibrium stationary state. Okay, so this reaction diffusion model has non-equilibrium stationary state. And remember, how do we check that a system is non-reversible? You just have to find a cycle on which going in one direction has a different instantaneous rate than going in the other direction. Okay, so if you look at this cycle here, you'll see that so for example, this transition here has an instantaneous rate alpha plus lambda over 2. This one here is n squared because it's an exchange, and this one is an annihilation, so it's b. So the going in that direction gives you 8 plus lambda over 2 times n squared times b, and going in the other direction gives you a times n squared times b. So this loop here is a non-reversible loop. Therefore, the invariant measure of the system is non-reversible. So you see, checking that irreducible Markov chain does not have a reversible invariant measure is not so complicated, because you just need to find one non-reversible loop.
I have a question.
Yes.
I don't know what it means for invariant measure to be non-reversible. Does it just mean that the chain is non-reversible, or does it mean something else?
Yeah, it's exactly that.
Okay, thanks.
Okay, so the reaction diffusion model has well-studied hydrodynamic behavior. Okay, so the idea is that since interactions are local, when you look at the density of particles, I don't want to be precise about what do I mean by the density of particles, so you can cook up in your mind your favorite definition for that. You can take I don't know, balls of size square root of n and take the average of particles there and call that the density of particles at some particular point, doing something like that. Whatever you do is probably going to be okay as a legitimate definition for what the density of particles is. Okay, so we want to make it dependent on both time and space. Okay, so that's the only thing. And we want to think about this discrete torus as a numerical approximation of the continuous torus. Okay, so remember that we have in our mind that the distance between neighbors on the discrete torus corresponds to distance of order of size 1 over n in the continuum. If you do that, you see that the discrete torus can be embedded into the continuous torus. Okay, and it's in this continuous torus that this density lives. And to establish the hydrodynamic behavior of an interactive particle system means to find the limiting evolution of the density as in this torus. And usually what you find out is that when interactions are local, what turns out to appear in the limit is PDE. So the density of particles is governed by a partial differential equation. So the density of particles is a solution of a partial differential equation. This is indeed the case for the reaction diffusion model. And the equation that appears is the reaction diffusion equation. Okay. So the equation there is called the reaction diffusion equation. Okay. So without the F, it's the heat equation, and that's one particular instance of a diffusion equation. Diffusion equation, it means that mainly the diffusion coefficient in front of this heat equation depends on something else. It depends on time, on the space, or even on the function u itself. In that case, it's a linear diffusion. And in this particular case, we don't really want to be super technical, so we really want to have the heat equation there, so to reduce technicalities to a minimum. But in principle, you can do something more sophisticated. So this is a reaction diffusion equation. So that's the diffusion, the heat equation, and then the reaction is just a source term of the form f of u. That's what people call the reaction term. Okay, and this type of equation appears a lot in chemistry, for example, where you have reactants that react, and then there is not a conservation of one particular reactant, but there are conservation laws, general conservation laws, there are conservation of mass, energy, etc. But if you look at the concentration of one particular element, that might not be conserved. And in our particular case, the function f can be computed in a rather explicit way, and is equal to that. Okay, so let me just remind you what were the rates. So remember that so we were annihilating particles with rate b, and we were the other way around. So we were creating particles with rate a plus lambda over 2d, the sum over y neighbor of x, sigma y. Right? Yes?
Can you just press tableau droite there so that the remote audience can see it?
So tableau gauche or droite?
Droite.
So these are the rates, and you see how this function f is computed. Okay, so how do you lose mass? Well, first you need to have a particle. So if you believe that this density u is the density of particles, that happens with probability u, and then you have the rate at what happens. So you lose mass with that with this rate, okay, and you create mass with this rate here. So you need a hole. So you believe in this picture, that gives you 1 minus u, and then if you believe in this picture, these guys here are like 1 u, no, 1 extra u. So you have 2 to the, so this 2d is there. You guess why? Just to give you here lambda u. Okay, and you see that the function f is just the addition of these two effects. Okay, and this is the function f, and you can check that this function f has exactly 1 0 on the interval 0 1. Okay, so you can check it 2 ways. You can actually compute it It's just a second order equation, so we can actually compute it more or less explicitly. That computation is not very illuminating because, well, there are some radicals and stuff, and then you at some point you realize that if you write it in the right way, you get one root which is inside the interval 0, 1, and the other root which is outside the interval 0, 1. But probably something easier is just to observe that f of 0 is positive and f of 1 is negative. So you have to have 1, 0, and moreover, you have to have an odd number of zeros, right? And this is a second order equation. You cannot have, if it has an odd number of zeros, it's 1. You cannot have 3 zeros, right? Here you have to count multiplicities, of course. Okay, so a consequence of that, okay, well, an additional thing that you can check is that the derivative is different from 0. Okay, and this is again something you can just can check because of this geometric counting principle. Because if the derivative is also 0, it means that the 0 is double, no? And you cannot have a double 0, because again the number of 0 has to be odd. So the derivative has to be different from 0, and then it has to be negative. If it were positive, again, you have to have more zeros. And so the consequence of this fact is that when you run the, remember that this is on the top, so it's a very boundary condition. When you run your reaction-diffusion equation, the PDE, no, this is a PDE fact. You converge to U star. So I call it rho star there, so I probably should call it U star, or maybe call this one rho star. It's easier. Okay, so this guy rho star. Okay, so you converge to the guy, and this is a well-known fact in PDE theory. It's not very difficult to prove. Okay. Okay. Yeah, this is something I always forget to do. I should give some references. No? So yes.
Some question on the theorem. How do you yeah, how do you renormalize exactly in the convergence which is in the theorem?
So well, I don't want to be very specific about that because it's if you want to really be specific, then you get a little bit more technical, and it's kind of it's not really the real purpose of this. Later on, we will see one possible way to interpret this convergence, and we're going to actually prove a version of this theorem on which I will explain exactly what is the type of convergence that we're getting. Okay, but if you know about this, is you can think about convergence of empirical measure in the sense of measures. Okay. So now a little bit, references. Of course, no, you feel free to interrupt whenever you want. Huh? So this model, this reaction-diffusion model, was introduced by the Massey, Ferrari, Leibowitz in the 80s, and it was remarkable that they get kind of a very nice picture of what was going on. So they proved the theorem I just mentioned to you, and they also were able to prove the associated central limit theorem, because a PDE, from the point of view of probability, is the same as a number, right? It's not random, it's a deterministic object. Therefore, if you can understand this hydrodynamic limit convergence in the theorem as a large number, and a central limit theorem is the natural further step. And these guys, the Massey, Ferrari, Leibowitz in the 80s were able to actually prove that, the CLT. Okay, with the technology that was available in the 80s, that was really a remarkable fact. Okay, so later on, no, in '93, no, Jonalazino and Invares, they reproved this hydrodynamic limit, basically following Kidney-Sola-Varadan. Okay, so in '93 there were this Guo-Papanicolaou-Varadan theory of hydrodynamic limits available, which makes all this type of results somehow simpler to get in some sense. It's a more robust technology that really allows you to treat your favorite your favorite system with some up to some level at least, and they also proved the large deviations principle. This is interesting because this Wu, Papanicolaou, Varda, and Yau theory of hydrodynamic limits allows you to prove the hydrodynamic limit, which is a law of large numbers, and also allows you to prove a large deviations principle, but does not allow you to prove the CLT. That's kind of curious, because in the previous results in the 80s, people struggled a lot to prove the law of large numbers, but at the end of the day, if they were able to do it, usually they could also get the CLT. So our observation is that in this paper of '93, so this reaction-diffusion question didn't have multiple stable points. Okay, so as I mentioned before, I'm sticking to the simplest possible case on which you have just one fixed point for the function f. So if a function, so the stable points are the stable zeros of the function f, and in our situation we have only one zero, so that's the only stable point. So in principle, general landing variance applies for this model, and you can see that so Farfan, Landin, Tsunoda prove this result, the same things, hydrodynamic limit and large deviations, in the case of multiple stable points. And you can see that the time difference of almost 30 years. So you can see that multiple stable points is probably more difficult than just one stable point. Okay, so and all of these things that I've been mentioning here, they fit very, very well in the what is called macroscopic frustration theory in this nice theory by Bertine, Soler, Gabrieli, Jonas, and Landin. So also Derrida has something to say about this macroscopic frustration theory. And so what I'm quoting here is a paper in the Review of Modern Physics. So these guys, they wrote like I don't know how many papers, so it's difficult to quote them. So the easiest thing to do is just to refer to the latest review that they wrote. Okay, and that's the one that is nice, and it's a review on modern physics. So also this is the reference. Okay, so extra references. So if you want to know everything about the interacting particle systems and their scaling limits, you can go to Kidney's and Dick's book, Scaling Limits of Interacting Particle Systems. Then the relative entropy method was introduced by Honser Yao in 91 in a paper in Letters on Mathematical Physics, and most of what I'm going to present to you now, I have taken it from the PhD thesis of Otavio Meneses. Okay, so those are some references. Now there are tons of others reference for this topic. The reaction diffusion model is are really a very active field of research. Okay, so let's go back to the model. So let me do some computations with generators. Okay, so for the moment you don't need to read down there. So how do we guess at least what the hydrodynamic equation should look like? Okay, so remember that if you apply the generator to certain function f, what you get is the time derivative of that function f. Actually, you have to take expectations, no? But this is, morally speaking, the story. And so let's try to discover how the density evolves in time. So the first thing that you can do is to apply the generator to the function sigma x. Now, the function sigma x is like the local density. Okay. Maybe the local density, maybe you need to do an averaging to really get the density. But this is just to start us, no? So let's do this because well, there's nothing to lose, no? And then you do the computation. You see what L of sigma x is, and you get that expression there. And you see that you're starting, you see that you really get what you should get, no? Because the first term there is, it looks like a Laplacian, right? It's the value at your position. It's the difference between the value at your position and the average around your neighbors. So maybe there is 1/2D missing there in order to be the exact average, but that will carry on into 1/2D in the Laplacian as well. So it doesn't really matter. And in the second line, you get something which is very similar to the function f, right? So now let us define rho, okay, as expectation of that thing. Okay, so that's one possible definition of the density of particles. Okay, so I told you I didn't want to be very precise about what do I mean by the density of particles, because if one wants to be rigorous, then you have to be technical, and if one really wants to be give a nice intuition, then you have to define something which is not rigorous. Okay, so let's do this. Okay, so this is the non-rigorous part, and then the derivative of that expectation is the expectation of the generator applied to that function. And what you get is a discrete Laplacian plus some linear term plus some nonlinear term. And here you need to do some assumption, okay? So we should say, okay, you know what? Let's assume small correlations, okay? Why? Because, okay, at this point, this is completely unjustified. But if you're thinking afterwards to take average over the mesoscopic regions, let's say, and you really believe that the law of your process, since the dynamic is local, is reasonable to assume that the law of the process is kind of locally ergodic in some sense, okay, so it doesn't have long-range correlations. Whenever you do an average over a mesoscopic region, you probably will recover part of this small correlations assumption. Okay, so well, here you are just assuming because you want to see what happens. Okay, and then if you assume that correlations are small, then what happens is that you discover that this function rho tx really solves a discrete version of the hydrodynamic equation. It's exactly Laplacian plus f. Of course, it's not exactly f, right? Because if you assume small correlation, what you get is the product of rho of x and rho of y, not rho of x to the square. But then, if you really believe that the diffusion part is going to regularize things, then these two guys should be very close as well. Okay, so it's really a discrete version of the hydrodynamic equation. Okay, so this is the way on which you guess what the hydrodynamic equation will be. Okay, so this is the computation with generators that you can do. And now I've talked about the reaction diffusion, hydrodynamic limits, but now I remember that yesterday I didn't talk about anything of this. I talked about this idea of relative entropy applied to general Markov chains. So let's go back to relative entropy. So in this Gauss inequality, in this relative entropy method, if you want to, you need to define a reference measure. Okay, so what is the idea? So I kind of feel somehow I can guess that my process, the law of my process is close to this particular law. Why? Because, well, for some reason. Well, one way to prove that intuition is to use this Gauss inequality and see whether the relative entropy is, at the end of the day, small. Okay, so now you see the density of particles should follow this this discrete version of the hydrodynamic equation. Okay, so we're going to make a guess, and the guess is that the density of particles does follow this discrete version of the hydrodynamic equation. Okay, And moreover, we are going to make the following guess, that not only the density is given by the hydrodynamic equation, but moreover, sites are almost independent in some sense. Okay, so I assume that the correlation were small, so let's put as a reference measure a reference measure on which correlations are zero. Just to check. Okay, this is not saying at all that the law is really like this. Okay, so let me go back here. You see, assuming small correlation. So this is reasonable, but not known in general. Okay, so I don't remember. So well, I think Claudio proved this in some cases, no? Huh? Yeah. So you call it conservation of local equilibrium, no? Yeah. Yes.
But in the hydrodynamic equation, n square maybe should not be there, because the discrete Laplacian.
Okay, well, it depends on how you define the discrete Laplacian, of course. I mean, I usually write when I write discrete Laplacian, it goes without n square.
This Laplacian is the discrete Laplacian.
It's the discrete Laplacian. Yes.
Okay, thanks.
Yeah. For me, that delta is a discrete Laplacian at this point. Okay, so surprisingly enough, this is something that is not known in general. That if you take in this reaction-diffusion model, if you take two sides, well, maybe actually the massive array levels prove that if you take two sides, they are almost independent. So this small correlations property is true, but in general, I mean, for general reaction-diffusion models on which, for example, maybe the diffusion mechanism is nonlinear, this is really not known. So it is reasonable. It has been proven in some situations, but there is not general theorem tells you that it's actually true. Okay, but well. That's the magic of this relative entropy method. It doesn't have to be true what I just said, because at the end of the day, if the reference measures that you are putting there work, they work. If they don't work, they don't work. Okay, so if the reference measure you put there work, it means that it doesn't really matter how you guess them to begin with. So the Gauss ansatz is that good reference measures are these products of nullies. Okay, so in this case, on which the state space has only two sides, you don't have much room if you want to have something which is independent at each side. No, it has to be products of nullies. So you put that, and then I call it that leap of faith. Okay, so this measure mu t approximates the law of the process at time t. Okay, so let me do an observation here. So if in the PDE, at the PDE level, you start with something which is independent of t, then the Laplacian is automatically zero. So the solution, this reaction-diffusion equation becomes an ODE, an ordinary differential equation. Okay, it becomes so it's written there. So it becomes rho theta, rho prime equals f of rho. Okay. And this ODE, it has one stable attractor in the interval 0, 1. So whenever you start, you go there exponentially fast. Okay, so let's simplify things. So in order to continue with the computations, what I'm going to do is that I'm going to assume that the initial density of particles is uniform somehow. Okay, so I'm not going to assume that the density of particles of the real Markov chain is uniform, but I'm going to assume that my reference measures start with a uniform density. Okay, and we'll see where that leads us. Okay, so if you do that, then these Bernoulli product measures have all the same parameter. Okay, that is at the PDE level, the solution the PDE equation becomes an ODE equation. And also, if you check the discrete version of the hydrodynamic equation, if you assume that rho 0 tilde is independent of x, then the solution of this equation is also going to be independent of x at later times. Okay, so even though the function fn there is not a function only of rho tx, it's a function of rho tx and also their neighbors, this equation still have the property that if you start uniform space, you are uniform space for any later time. Okay, so both for the continuous PDE and for the discrete PDE, if you start uniform in space, the equation becomes this ODE there. Okay, so that means that our reference measure is going to be slightly simpler. And so now the plan now is to this Young inequality, this relative entropy method, for this model with these particular reference measures. Okay, later on, if we have time, we can discuss the case on which you start with something which is not uniform in space. Okay, so let's do that simplification. Okay, let's take x independent of let's take rho 0 independent of x. Here I should tell you a little bit a justification for this. Okay, so maybe you feel that we are somehow cheating because the most interesting behavior will be when you take will happen when you take a non-uniform initial conditions. But there is one particular situation, one particular problem, which is very interesting to tackle and on which this strategy is already meaningful, which is the non-equilibrium stationary state. Okay, so the invariant measure of this Markov chain is something that we don't know. And it would be nice if we can say something about it. But after all this discussion, it's pretty much reasonable to guess that the non-equilibrium stationary state, this invariant measure of this Markov chain, is going to have a uniform density. Because it has to be concentrated on this in this rho star. One strategy, one way to get information about this non-equilibrium stationary state is what we call the dynamical approach. So the non-equilibrium stationary state is difficult to characterize in a static way. So you have here your Markov chain. Tell me how the environment looks like. That's difficult. So something we can do, and this is also behind the idea of Markov chain Monte Carlo, is let us run the Markov chain until it gets to the invariant measure. If we can say something meaningful about the Markov chain for any time t, or at least for times long enough to get close to the invariant measure, then we can invert this sort. We can do some sort of exchange of limits. No, send n to infinity first, and then t to infinity. Get information about the stationary measure with this procedure. Okay, and if you want to do that, this is again like a Markov chain Monte Carlo. When you run a Monte Carlo algorithm, you can. Well, you're a mathematician, and for mathematicians, for some reason, you want to start from the worst possible case scenario. But if you're a practical guy, you don't want to start from the worst case scenario. You want to start from the best case scenario, no? So you really, if you really know something about your target measure, you use it at the beginning, and you start with that. And we know something about the non-equilibrium stationary state of this Markov chain, which is that it should have density rho star. So maybe a good idea is to start with Bernoulli rho star, our Markov chain, if we want to get information about the non-stationary and the non-equilibrium stationary state. And actually, this is something we can do. Okay, so that's part of. If I have time, maybe I can get there and show you how to get information about the non-equilibrium stationary state out of So remember that, so let me remember Gauss inequality. Okay, so Gauss inequality is h prime of t is less or equal than minus this guy here plus the integral of this function ft d mu t, where this guy ft is the density of the law of the process at time t with respect to the reference measure mu t. This guy here can also be written as the expectation of ft of the process at time t. Okay, sometimes if you're really good at probabilistic arguments, from here you just can show that this guy is small. Okay, and then you don't need to be super sophisticated, but that's not my case. And so I really need to work more with this guy here and slowly taking out information of it until I get something meaningful. So I really use more this representation here than the more probabilistic representation out there. Okay, but this is Gauss inequality. So the first thing that you have to do is to compute f of t, this capital F of t. Well, and there is a formula for that. Okay, so if you remember yesterday, so the formula was LT star of 1 minus that derivative. Okay, and that measures how far this quantity there ft measures how far your reference measures mu t are from satisfying Fokker-Planck equation. That's more or less the thing. So it really turns out to be a sort of quantitative. This function capital Ft has quantitative information about how good our guessing was to begin with. So well, one has to compute it. Okay, so this is not a short computation, but it's not also complicated. So I wrote it down. I don't expect you to follow it. I think well, the notes should be on the website, so you can check them later. Also, you can check my paper with Octavio Meneses if you're yeah.
Sorry, I was just wondering if the reference measure is Bernoulli a half or Bernoulli the target density or something.
Okay, yes. So here, so yesterday, if you remember, I told you that the new bar reference measure doesn't really matter, because at the end of the day, FT does not depend on that. So here you put whatever is the easiest for you. Okay, so well, for me is Bernoulli 1/2. Okay, and then you go and in fact, I think I did the computations with Bernoulli row 0. Yeah, maybe row 0. Maybe your suggestion is better than 1/2. So maybe well, yeah. Well, as I told you, it doesn't really matter. So maybe let's put here. Good. So and then you compute. Okay. And then and you cross your fingers. So I've done these computations like 1,000 times. So for me, this is obvious nowadays. And it's obvious that writing in this particular way is the right way to do it. Okay, so well, this is nice. No, this one is easy. No, it's linear in the random variable sigma, so it's easy. That's a computation, and you can do it at home if you want to with a little bit more freedom. And this is the other one. Okay, so this is uglier. So this is a clear oversimplification. So of course I knew very well what I was doing. So that's what it is. So let's talk a little bit about some particular pointers. So things which are important in these computations. Okay, so the first thing is that the first line, it's explicit. Okay, that's really good. Okay, so it's really something that you can compute explicitly, because mu t is the Bernoulli of density rho t. So computing this quotient there, this ratio is very easy. It only depends on sigma x because you're only changing one guy and all the other guys remain the same and the measure is product. So it's a very simple computation. Maybe you can, well, it takes some time to actually do it, but it's not difficult. And this CX, they are also explicit. One additional that I didn't mention, but now I can mention it, an additional feature of this computation that makes it even simpler is that the exclusion part does not play a role there. Okay, because the product measure, this Bernoulli product measure of constant density is actually an invariant measure for the exclusion process, which means that the exclusion part applied to the constant function equals to 1 is equal to 0 because it's an invariant measure. It means the L star of the exclusion part is again the exclusion process, which is the generator Markov chain. So that's an additional layer of simplification. So you only have to worry about the reaction part, and then you do the computation. And in this computation appears exactly f of rho. Okay. And actually, what really happens is that you choose the equation for rho t in such a way that this term will cancel with the other one. So that's the way on which you actually choose the density, the equation for the density. Because so here you see, so in this last expression, in this last sum, you have a linear part and a quadratic part. Okay, so I think about this as polynomials on the random variables, on the center random variables sigma x minus rho. Okay, so these are center random variables, and f rho t times that guy there, it's a polynomial of degree 1 on those variables, and the second sum gives you a polynomial of degree 2. Okay, so it has to be a polynomial of degree 2 in these variables because the rates are polynomials of degree. Okay, so you can check that you cannot get higher order terms than degree 2, but that means that you can have a zeroth order term, you can have a linear term, and you can have a quadratic term. The zeroth order term always cancels because you can check that the expectation of the function capital F is always equal to 0. Okay, so that means that here in the zeroth order term, the constant term has to cancel because the constant term is expectation. And then you get the linear term and the quadratic term. And the idea is to cancel the linear term with this guy here, right? So this guy here gives rise to a linear term and should cancel this linear term here, right? So that's how you choose the equation for rho t. So you do that, and what is the conclusion? The conclusion is that the function f is that thing there. So it gets a very simple and close expression. So what is important about this expression here is that that does not have terms of degree 1. In this particular case, only has terms of degree 2. It could have, for more complicated reaction dynamics, it could have terms of degree 3, 4, and so on and so forth. But the main thing here is that all terms in this sum there are of degree at least 2 on the centered variables sigma x minus rho. That's the important thing. Okay, we'll see that later. So as I was telling you, the zeroth order term cancels, and the first order term cancels because we chose the density rho t in such a way that it satisfies the discrete hydrodynamic equation. So now I'm going to give you, I wrote this vague idea. So this is a very, very vague about why having a term of degree 2 is good. okay, is that if we believe in the picture I was telling you before about densities, it should be possible to show that actually this term of degree 2, this product of two guys, is close in some sense to the density of particles on a box of size L to the square. Okay, so this is what people call the replacement lemma, or replacement step, or replacement theorem, whatever you want to call it. Is that if you have in your system a nonlinear function, you can replace the nonlinear function by a nonlinear function of the density of particles. Okay, so if you have something which is in this case, is sigma x, sigma y is not a function of the density of particles, because these are just two sides, so it's too singular to be a function of the density of particles. But somehow you want to show that you can replace that term by the density of particles. And in that case, it's going to be the square of the density of particles, because you have two terms. And if it's a square, you win something. So you see, so here I made a mistake that I wasn't supposed to make, but it's good because I can explain you something. So if you believe in this idea that that a local function should be a function of the density of particles, if this function were linear, you can replace it by the density, but not the density square. And then in this O here, you will have what I wrote. No? It will be of order 1 over L to the d over 2, because of the CLT. No? What is inside should satisfy the CLT. Therefore, it should be, if you normalize by L to the d over 2, should converge to something non-trivial. So you're normalizing by 1 over L to the d, so you're winning something. How much you're winning? L to the d over 2. But actually, you're winning L to the d, right? Because it's a square. So this L to the d over 2 gets squared. Yes? Maybe you want to, yeah, you should.
Why is it lambda over d? I would have expected lambda over 2d. Or maybe I missed something in the rest of the calculation.
Maybe you're right, maybe not. I'm not completely sure. I don't remember if I'm using here ordered pairs or unordered pairs. So there could be a factor of 2 because I'm using unordered pairs. But I believe I think that morally speaking, what appears there is going to be related to the derivative of the function f. And in the function f, you have this term lambda times rho square. So when you derive it, you get lambda, you get 2 lambda rho.
But if I look at L stat t applied to 1, the lambda over 2d is there.
Yes, but
and so you say that in the derivative of the log of the measure appears the same term, and that they add?
Yeah. So it appears the same term in the linear part, so they cancel. And in the quadratic part, there's going to be a factor. So in the linear part is multiplied by f of rho. The second order term, the quadratic term, is multiplied by f prime of rho, basically. And then f prime of rho has a 2. And that's why here you have lambda over t and not lambda over 2d. Yeah, well, I mean, I might be wrong, but I believe I'm correct because of that argument. Because when you take the derivative of f, the rho square throws you a factor 2 in front of the guy. Actually, it's not super important because, well, it might be important in some situations, but here it's not going to be very, very important. Okay, so the vague idea is that you can make this replacement. Okay, and this is so I think, although I think I still have like 7 minutes left or something. I think now is a good point to stop. Let me just tell you what I'm going to do on Thursday. So for Thursday, so what I'm going to do is that up to here, everything has been very, very soft, in the sense that I made computations, but nothing really substantial. So now what I just I mean, at this point here right now. So here I have the expectation of the sum over x and y of lambda over d. So let me call it, I'm running out of space, so let me call it just a sigma bar. Okay, so this is what I get here. And at some point, I should start to use this negative part. And the idea now is to replace this guy by the square of the density of particles, paying a price given by this energy that I have here. So that's the idea. So if you can do that, so and that's why I don't like, or that's why I don't use directly this interpretation of this guy as the expectation of this, but I go back to this as integral of ft d mu t, because now I do what people do in PDEs. This is what they do now. Once they derive some a priori estimate, they say, okay, now let's forget about ft. It's not really important that ft is really the solution of my evolution equation I'm looking at, because now it's a game of energy. No? So I have this sort of energy here. How can I improve here this term here using the energy I have on the other side? So and that's the game that we are going to play on Thursday, and we are going to see that this vague idea can be actually implemented and put into a rigorous theorem. Okay, so that's the plan for next time. Thank you very much for your attention. One more time, if you have further questions, I will be glad to answer.
Thanks very much, Milton. Are there any questions from the room or from the remote audience?
Yeah, I had a question as to, because you're doing this mesoscopic, scaling. So are you losing sort of the structure of the lattice, like where in terms of the description of the? So like if you put some other structures as a local topology really matter? I mean, you'll do a different scaling, of course, if it's not D and it's like a hexagonal lattice or something like that. But do you see what I'm saying? Are you sort of doing a sort of mean field because you're getting this essentially, correlation decay?
Yeah.
Right. So I guess another way to think, you get a similar equation if you did this on the complete graph.
Yeah. So at some point I have to prove something. No? I have to prove this part here, no? And there, what we really use is basically the fact that it's the behavior of the green function on the lattice. At some point, that's going to play a role. Okay, because we want to. At some point, what we are trying to do is that you have a point mass that you want to spread over a mesoscopic region. So there is a transform problem that you want to solve, and this transform problem can be solved in terms of the green function of your random walk there. And now the question is, does the cost of let's say in a sense the capacity or the energy of that flow that you use to solve this optimal transfer problem can be estimated by this guy or not? Okay, so the answer is yes, up to a certain mesoscopic scale, and that is actually what fixes the scale. So if you are in a, even if you are in a more complex structure, maybe a tree or the complete graph or a sparse graph, if you have information about this transfer problem, which amounts to have information about the green function of the random walk on that graph, then this sort of idea can be implemented.
When people talk about local equilibrium, is this thing that is said to prove that the Bernoulli with the profile is close to the law of the
exactly. Yeah. That's what people call local equilibrium. Well, Depends. I mean, it's not also a consensus in the community. So historically speaking, what people call local equilibrium is that there's the following. Let's look at a box of size 10 by 10 of our system, and let's look at the law of the particle system there. And the question is, does this law looks like a Bernoulli product measure or not? And that's local equilibrium. Okay, so it's a different question that's saying that globally the Bernoulli product measure it's a good approximation, because it could be that globally is a good approximation, but if when you fix one particular box, it happens that there is bad. Okay, so that historically speaking, that's the definition of local equilibrium. Then when you try to prove things, you discover that maybe that's not exactly the thing that makes sense. You prove another thing, which is, well, maybe it's what you can prove, maybe it's what it makes sense, and you call it local equilibrium as well, because it's related to the previous notion.
Sorry, I didn't understand when you talk about the fact that you assume small correlations. When does that appear in the reasoning? I mean, when you do the replacement, I don't know where do you...
In the proof, is not going to appear anywhere. The only thing, it only appeared to give the ansatz about the Bernoulli reference measure. Okay, so you think, well, if correlations should be small, then maybe correlation 0 is a good starting point. Maybe later on I can improve my reference measure to put in some correlations, and maybe that works better. This is something that might or might not happen. But it's just an intuition that one has, because maybe somebody told you that. But it's some sort of intuition that gives you a starting point. That could be right or wrong, but at the end of the day, we don't really use that. We don't even prove that. So we can prove a soft version of that fact. So for example, in dimension 1, what we can prove is that if you average over any slowly increasing region, then correlations vanish. So you take a region of size log n, another region of size log n, you take the means, the average there, and you look at the correlations. Those correlations decay.
And how fast? I mean, how fast?
I'm not sure. I don't remember exactly, but we have some estimates. Probably there will appear on the course. Okay, so we have some estimates, and from this estimate you can have some estimates about your questions. And I'm not complete that now. I don't remember exactly what our estimates imply for your question. So the question down.
I was wondering, this local equilibrium, when you have a product measure of Bernoulli, but you could have local equilibrium with some kind of short range correlation.
Yes.
So it will not be Bernoulli.
No. No, yeah. I mean, for this particular problem, Bernoulli happens to work, right? But for example, I think Benoit, where is Benoit? Somewhere there, no? He proposed another type of local equilibrium measures that work for him, and that's perfectly fine as well. So somehow the idea is that this, at least as first order, the Bernoulli should be good enough. If so, I don't know if I'm going to have time to explain the scaling limit of the non-equilibrium stationary state. But if I have time to do that, we will see that the non-equilibrium stationary state has long-range correlations. So it's not only short-range correlations, so it's long-range correlations. But the information we get using these per product measures, which are not such a good approximation at the end of the day, it's good enough to prove that that theorem about correlations in the non-equilibrium stationary state.
Okay, I didn't see any questions online, so that's all. Thank Milton again for a very interesting second lecture.
Thank you.